there is a crisis in the cosmos, and the fate of the entire universe depends on it. We have known that we live in an expanding universe since 1929, when Edwin Hubble demonstrated for the first time that galaxies move farther and farther away over time. This expansion has become the foundation of all our theories of cosmic evolution, from the Big Bang to the formation of galaxies. The key factor is the rate of expansion of the universe, a value known as the Hubble constant. We believed this value is fairly fixed, but now astronomers are not so sure. We find ourselves on the brink of a cosmic revolution, or it could be that our entire model of the universe is wrong, as we explore the crisis-shaking cosmology and discover how Hubble's greatest discovery has become one of the most troubling questions of today. For most of human history, the universe was small, or at least that's what we believed. Some ancient civilizations imagined the Earth as flat and covered by a dome of stars. The sun and the moon rose and set, and the constellations rotated above our heads. By the 1st century, astronomers such as Claudius Ptolemy had conceived a geocentric universe with the Earth fixed at the center, and the sun, moon, planets, and stars orbiting around us. This would be the predominant model for more than 1,000 years, until in the 15th century, Nicolaus Copernicus proposed a heliocentric model in which our Earth was one of several planets orbiting the sun, a revolutionary idea. Fast forward to the 17th century, William Herschel mapped some of the stars of our galaxy, the Milky Way, showing that it was a vast disc-shaped system. Although it seems outdated today, astronomers debated for a time whether the Milky Way was the entire universe or whether it was in fact one of several island galaxies in a much larger cosmos. This was the case until 1923, when Edwin Hubble settled the question once and for all by observing through the 100-inch Hooker telescope at the Mount Wilson Observatory in California, the largest telescope in the world at that time. Edwin was able to distinguish individual stars in Andromeda, and within them he found his first Cepheid variable, using Leavitt's law named after Henrietta Leavitt, who discovered more than 400 variable stars that could be used to measure distances in the universe. Hubble determined that Andromeda was about 900,000 light-years from Earth, an astonishing distance, far too great to be part of the Milky Way. This showed that another galaxy with its own stars existed outside our own. Overnight, Hubble expanded our view of the universe immeasurably, but he didn't stop there. He used Leavitt's law to identify another 23 galaxies and measure their distances, some up to 20 million light-years from our planet. Eventually, Hubble concluded that millions of galaxies must exist beyond our own, which changed astronomy forever. But Hubble's next revolutionary discovery also required the work of Vesto Slipher, an astronomer born on a farm in Indiana in 1875. He joined the Lowell Observatory in Flagstaff, Arizona, in 1901, and between 1912 and 1925 carried out systematic observations of more than 40 spiral galaxies. At the time, it was known that the light observed from these distant galaxies could be broken down into its spectral components, and that depending on the elements present in the light source, different patterns would appear. If the observed object was moving away, those same patterns would still be present, only shifted toward the red end of the spectrum, what we call redshift. After years of observation, Slipher discovered that almost all galaxies appeared to be moving away from us, but at the time he had no way to measure the distances to these distant bodies, much less their speed. In 1927, the Belgian scientist Georges Lemaitre proposed the theory that the universe was the same in all directions, and that if Einstein's theory of relativity was correct, it must also be expanding. But he had no evidence to support this theory, so it was largely ignored. This changed when we returned to using Hubble's telescope. Like most scientists of the time, Hubble was unaware of Lemaitre's theory, as well as another similar one proposed a few years earlier by the Soviet scientist Alexander Friedman. From the Mount Wilson Observatory, Hubble made the same observation as Slipher, that galaxies seemed to be moving away from us, but he noticed something no one else had seen before. The farther away a galaxy was, the greater its redshift, meaning it was moving away from us at a higher speed. And this happened in all directions. Subsequent observations revealed that almost all galaxies seemed to be moving away from one another, and that the redshift of the galaxy was directly proportional to its distance from Earth. This was a major breakthrough. It meant that the universe must be expanding. Hubble announced this finding in 1929, and after its publication, it became evidence supporting Lemaitre's theory of an expanding universe, which would come to be known as the Big Bang. Hubble's initial measurement of the rate of expansion of the universe, which would become known as the Hubble constant, was approximately 160 kilometers per second per million light-years. This is equivalent to about 500 kilometers per second per megaparsec. However, this value was not entirely accurate, and even Hubble himself worked to refine it throughout his career. Since then, the Hubble constant has become a fundamental value in cosmology. We have used it to determine the age and size of the universe. And these data are important for many, if not all, other cosmological calculations. To obtain the most precise value of the Hubble constant, astronomers have used two main methods. But something about this value doesn't add up. One way astronomers measure the Hubble constant is through additional observations of redshift. In other words, in the same way Hubble made his initial discoveries, known as the cosmic distance ladder or late universe method, it measures the expansion as we observe it now, billions of years after the Big Bang. The more distant redshift examples we can obtain, the more precise the measurement. Over the years, this method has refined the Hubble constant to approximately 70.135 kilometers per second per megaparsec, a value significantly lower than Hubble's original one. The other way to measure the Hubble constant is through the early universe method, a more recent technique that estimates the expansion by going back in time to the beginning of the universe. This method is based on images of the cosmic microwave background, an ancient microwave radiation that essentially is a snapshot of the universe about 380,000 years after the Big Bang. This cosmic microwave remnant had been predicted in 1948 by Ralph Alpher and Robert Herman. Arno Penzias and Robert Wilson detected its presence in the 1960s, winning the Nobel Prize for their work. However, it was not until later that we obtained a sufficiently detailed image to predict the age of the universe with precision. In 2003, the Wilkinson Microwave Anisotropy Probe published an all-sky map showing the early universe, a time even before the existence of stars. Imagine that you arrive at the site of an explosion that has already occurred. You see fragments scattered everywhere and cannot tell what the original object looked like. But then someone shows you a photograph taken just after the explosion began. You could now trace each fragment back to its corresponding place in the original image. This is similar to how astronomers use cosmic microwave background radiation to trace our current universe back to just after the Big Bang. More recently, in 2013, the European Space Agency's Planck cosmology probe managed to capture an even more detailed image of the entire sky of the background radiation, showing subtle temperature fluctuations that over time would propagate to create networks of dark matter, forming galaxy clusters and voids throughout the universe. When astronomers take the image of the cosmic background radiation and rapidly project it forward to the present, it is like replaying the video of the explosion. They obtain a predicted Hubble constant of approximately 60.74 kilometers per second per megaparsec. But this value is considerably lower than the Hubble constant observed through redshift, which is a problem. It is essential to emphasize that the expansion of the universe has become a pillar of our standard cosmological model. The Hubble constant is tied to our most fundamental physics, from Einstein's theory of general relativity to the idea that the universe evolved from an initial dense and hot state known as the Big Bang, also known as the lambda cold dark matter model, or lambda CDM. It emerged in the late 1990s and since then has worked perfectly. One important feature of this model is that scientists expected gravity to slow the expansion over time, but instead they discovered that it is now accelerating it. Fortunately, this did not invalidate the model. Something seems to be expanding space faster and faster, and we believe that something is dark energy. As the universe grows, the effect of dark energy intensifies, causing galaxies to move away faster and causing the Hubble constant, the expansion rate of our universe, to increase over time. Both methods for calculating the Hubble constant aim to give us the current rate of expansion, though it is not this acceleration that causes the difference in results. But how can we have a unified cosmological model with two different values for such a fundamental rate? This discrepancy is known as the Hubble tension, not because it represents a real tensile force, but because of the atmosphere it generates at cosmology meetings. It could mean that our entire cosmological model is wrong. It was believed that as more precise data were collected, these two values would converge to an agreed-upon value for the Hubble constant. But that is where the problem lies. As we have obtained more recent independent redshift measurements, the value does not converge. Instead, the discrepancy is widening. One independent measurement came from galaxies that host megamasers. These galaxies contain certain molecules such as water vapor that can amplify microwave radiation near a black hole at the center of a galaxy. This can create a maser, similar to a laser but with microwave radiation instead of visible light. Megamasers are extremely powerful, and their microwave emissions can be mapped precisely with telescopes. This means they can be used to measure the mass of the black hole and provide a very precise geometric distance to their host galaxy, allowing us to calculate the Hubble constant with a presumably very accurate distance measurement. In 2020, astronomer Don Pess and others used this method to measure a Hubble constant of 73.9 kilometers per second per megaparsec with 95 to 99% confidence. In other words, they were very sure. In late 2024, another investigation conducted by Daniel Skolnick, Adam Riess, and others produced an equally surprising value. They used data from the Dark Energy Spectroscopic Instrument to study 12 distinct Type Ia supernovae scattered throughout the Coma galaxy cluster about 320 million light-years away. What they found was a Hubble constant of 70 t/s by kilometers per second per megaparsec. More recently, in 2005, researchers from the Inter-University Center for Astronomy and Astrophysics in India used Mira variable stars in our galaxy as reference points to measure the distance to Mira variables in distant galaxies, a method similar to the one originally used with Cepheid variables. They found a Hubble constant value of 73 kilometers per second per megaparsec. All of these recent measurements roughly agree with one another, but they lie well above the margin of error of the Planck measurements based on the cosmic microwave background. It therefore appears that something is missing from our understanding of the universe. Astronomers, including two who worked on the Desai research, have raised the alarm. The lead author of the paper, Skolnick, a physics professor at Duke University, stated, "Our cosmological model may be failing," and noted that the Hubble tension increasingly resembles a Hubble crisis. Without a solution, the model we use to interpret the universe wobbles. Everything from when galaxies formed to how galaxy clusters evolve, and even predictions of the cosmic future is at stake. If the Hubble constant turns out to be the lower value calculated from the cosmic microwave background, then we live in a 13.8 billion-year-old universe that will likely continue expanding indefinitely, a stable and predictable future with constant dark energy. But if the Hubble constant is the higher value observed from redshift measurements, then our universe may be expanding faster than the current model predicts, and things could be stranger than we thought. In that case, our universe could be younger, with an approximate age of between 12 and 13 billion years. This could mean that we are missing something fundamental in our understanding of the early universe, dark energy, or relativity. Some scientists have proposed that radical adjustments may be required to reconcile the Hubble tension. These proposed adjustments include ideas such as decaying dark matter or dark energy that varies over time. The idea of modifying the equation of state of dark energy has even been explored, which would represent a possible change to general relativity itself, something that could force us to reevaluate our understanding not only of the cosmos, but of physics. But another recent idea is gaining ground, one that could save our cosmological model without rewriting physics. And all it needs to work is a small twist. Seriously, a 2025 paper suggests that we may have overlooked a very slow rotation, or spin, of the universe. Published by Balazs Sigeti, Isfan Sapudi, Imre Bartos, and Gergely Gaber-Barnafoldi. The idea proposes that a very slow universal rotation occurring once every 500 billion years would be slow enough to go unnoticed, but significant enough to affect how space is expanded over time. In fact, their preliminary calculations showed that this slow rotation could validate both values we have for the Hubble constant. By introducing rotation into the model, a lower expansion rate is predicted for the early universe, similar to that obtained from cosmic microwave background calculations, and a higher expansion rate is predicted for the current universe, similar to that obtained from redshift measurements. These are exciting initial results. Sapudi, one of the authors of the rotating universe idea from the University of Hawaii, paraphrased the Greek philosopher Heraclitus of Ephesus when explaining the hypothesis, citing panterai, meaning everything moves. And indeed, given how promising the initial results are, it could be true, including the entire universe. However, the authors clarified that this is only a preliminary calculation focused solely on the Hubble constant. The next step to solidify this idea will be more complex models and simulations that allow the hypothesis to be tested against other observations. This idea reminds us that there is still much to learn about our universe, but it is too early to discard our entire model of cosmic evolution, especially when we may be on the verge of understanding the missing piece. And even if we could preserve our cosmological model, this would imply a new rotating variant in which cosmic parameters and values would adjust to our new reality. In addition, this idea has another major advantage: it does not violate any known physical laws. On the other hand, we very much like the idea that not only our planet spins and our solar system rotates, but also the Milky Way and the entire universe.